All right, everyone, let's spend a couple minutes reviewing the stuff that we did yesterday while I wasn't here, the stuff that you watched the podcast on yesterday. Basically, the whole two-dimensional interactions, collisions, and explosions with funny angles. Okay? Real quickly, we'll just set up a situation where we don't have a funny angle, where we've got 90-degree angles. Okay? We won't do the whole question. We'll just set it up. Okay, in a situation like this, we've got to break it up into x and y components, where pi is equal to pf. And then we got to say m1 v1i plus m2 v2i equals mvf. Two objects before, one object after. One of these terms disappears for the x component. Which one is it? m1 v1i or m2 v2i? m2 v2i because, how come? And why does m2 v2i disappear in this equation right here? He's right, by the way. He was good. We're paying attention only to the y-axis, sorry, to the x-axis here, and that is entirely on the y-axis. Now, we don't know what its value is. Okay, we're not going to worry about that right now. Okay, if it's 10, 20, whatever, it doesn't matter. That term still disappears because all of it, however much it is on the y-axis. Nothing else disappears. We plug in our numbers, and typically at this point, we're going to solve for VF. Although, if the question asks you not for the final velocity, but for the final momentum, you could still solve for VF, or you could just say, you know what, let's just make it PF and solve for the x component of the final momentum instead of the final velocity. Does that make sense? That would just be a bit of a shortcut for you, right? If you're looking for final momentum, then you could use momentum in this question and not have to worry about multiplying it by m at the end. Usually it's velocity though, so we'll leave it as mvf and we'll solve for vf, whatever it would be. Okay, for the y component, we have the same two terms, m1 v1i plus m2 v2i equals mvf. One of these two terms disappears as well. Which one is it? Macaulay, which one disappears this time? Good, how come? Yeah, we're looking for the y components here now, and object number one is only moving on the x-axis. So we're going to solve for VF there. Now we've got an x component of VF, we've got a y component of VF, and then we're going to combine them by drawing a right angle triangle using the Pythagorean theorem in the inverse tan function. We're good with that? All right. So let's take a look now at a situation where we have a funny angle. So it might be something like this. Okay, we've got car number one moving up at an angle like this. Okay, let's say it has a mass of 1,000 kilograms and a velocity of 10 meters per second. Let's say we get car number two moving up like this. Let's make our angle 30 degrees here. Okay, let's make it a mass of 1,500 kilograms. And let's make its velocity 20 meters per second. So a heavier car moving faster. The wreckage, say it sticks together again. The problems aren't any harder if they don't stick together. I just make them usually so they stick together because they're easier to make up. They're not easier to solve. They're just easier to make up. If they stick together, so it's going to be an MVF term. But if they didn't, it would just be M1 V1F plus M2 V2F. All right, there's the final wreckage. It's going to go to the right, and it's going to go up. And we want to find out exactly what the speed is and exactly what the angle is there. All right, 5 words that we look at this question and say, I don't like funny angles. I don't like funny angles. 90-degree angles, 0-degree angles, 180-degree angles are much easier to deal with than 30-degree angles. So if I don't like funny angles, if I'm that dead set against funny angles, then let's just get rid of it. That 30 degrees, let's take it away. But to take it away, we have to do a little math. The first thing we do is make a triangle out of it. A triangle that surrounds the 30-degree angle. Solving for x, x is the adjacent side of the triangle. Adjacent and hypotenuse give me cosine. And 30 times cosine 30 degrees is going to give me, is it 25.33? 25 point something. 25.98 meters per second. So we'll do the same thing for the y component, except use sine for this one. Sine 30 degrees is equal to the opposite side over the hypotenuse. Y ends up being equal to 15 meters per second there. So if I want to, I don't have to do this next step, but if I want to, I can replace this vector that we see right here at 20 meters per second, 30 degrees. I can replace it with 25.98 to the right and 15 up. Now I don't have any funny angles. I've got two vectors, but one of those two vectors is split into two. So it's kind of like I got three vectors now. Jake? Multiplying by 30. 30 sine 30. 30 sine 30 would be 15. What's it, 20? Oh, why would I be using 30 then? Nobody wanted to point that out after the first one? Thank you, Jake. You got 17.33. 32. 20 sine 30 would be 10. Thank you. So now let's change this now. This x one turns into 17.32. And the y one turns into 10. So still same scenario, just a little bit different numbers here. Okay, so now we go and do exactly what we did in the last question. We got our x's and our y's. Pi is equal to Pf. M1 V1i plus M2 V2i equals, they stick together, so it's MVF. If they didn't stick together, no big deal. M1 V1f plus M2 V2f. M1, 1,000 kilograms. V1i is going to be 10 meters per second. M2 is 1,500 kilograms. V2i, tell me what that is. What's V2i? Unless I made a mistake. Tell me. 17.32. Right? The 10 meters per second is irrelevant because that's the y component. I don't need to worry about that 20 meters per second that I had originally. It's gone. Right? As soon as I got it into an x and a y component, I threw away the 20 at 30 degrees. I don't like the funny angle, so I completely got rid of the funny angle and anything that went along with it. Now I've got just an x and just a y. The final mass is 2,500 kilograms. And you're going to solve for VF there. Solve for VF. Now, when you're doing the y component, the initial momentum for the y component will be 0. The initial momentum for object number 1. For object number 2, it will be 1,500 times 10 this time, not 17.32, because we're looking for the y component. Equals 2,500 times VF. So what's the difference between these two questions, the one that I did in blue here and the one that I did in red here? There's only one difference. This little bit over here. Okay. I had all the x's and y's over here. I had to get all the x's and y's over here from the funny angle that I had. Okay. So this is, what is this, grade 9 math right here? Grade 9 or grade 10, whenever you guys did trigonometry for the first time? Okay. That's all this is. The only difference between this question and this question is grade 9 math. Sine, cosine, tan. Yep. I'm sorry? Yeah, you do. Yeah, you do. This is the y-axis down here. I just didn't want to really completely solve the problem. I just wanted to give you the steps in it, basically. So we do the x component. We solve for VF for the x component. Then we did the y component down here. The y component of object number 1 was 0. The y component of number 2 was 1,500 times 10, which is right there. And then the final was 2,500 times VF. So we'd solve for VF x component, VF y component, and then we combine them using the Pythagorean theorem and the tan function. Yep. Yep. Well, to be honest, I wouldn't put it on that diagram because that's the final velocity. You could, if you wanted to put it on the diagram, you'd put it right there. The x component of VF would be right there. The y component would be right there. I probably wouldn't because it starts looking a little cluttered after you start drawing too much on it. I'd probably just redraw it as a right angle triangle. Here's my x, whatever it worked out to be. Here's my y, whatever it worked out to be. Let's just do it on a separate diagram and figure out what v is that way and what theta is that way. Okay? All right, you guys had 4 questions for homework on worksheet number 4. You got the answers to the first 2 of them up here now. Take a peek at those. Now let me know if there's either of those that we need to go over. I'll put the second 2 up, question 3 and 4, in just a moment here. Question 3 up on the board now. Looks like I've got some changes that I made a mistake at some point in there. Looks like the answer that it should be is 21.2 and 2.12 and then 31.9 degrees. So I'm not sure what my mistake originally was, but something. And finally, question number 4, the last question that was assigned for homework. This was one of those funny angle ones, right? Question number 4. 75.1 at 62.6 degrees north of west. Okay. Got a request to go over number 4. The other one's okay? 3 and 4. Okay, now let's go over number 3 first. It's one that's slightly easier here because we've got just 90-degree angles right now, no funny angles. But it's a little bit different, Jace, in that we have momentum given to us instead of velocity, right? So not crazy hard, but still just a little bit of a change. This is a 4-kilogram ball traveling north with a momentum of 11.2. Let's make this object number 1. Its momentum is 11.2 kilograms meters per second. Its mass is 4.00 kilograms. We got another ball that's traveling to the west with a momentum of 18. We'll call that ball number 2. It has a mass of 6 kilograms and a momentum of 18 kilograms meters per second. So we don't know what the velocity is for either of these balls, but that's okay. You'll see in a minute how it doesn't really matter. They stick together, so the final velocity of this wreckage, the final momentum of this wreckage, is going to be up and to the left. All right, if we had a funny angle, we draw our little aside over here and resolve it so that turn it into x's and y's. We've already got all the x's and y's here, though. So let's start with the x's. Now we got 2 objects, m1 v1i plus m2 v2i. They stick together, actually, don't they? So let's just call it mvf with final momentum. M1, 4 kilograms. V1i. Okay, who can tell me right now, even though we're not given the velocities, what V1i is for the x component? Fraser, how fast is this guy right here, even though I don't know what the velocities are? How fast is it moving on the x-axis? 0. So we're going to cross that off. It's moving only on the y-axis, right? M2 V2i. M2 is 6. What's V2i? How many people said, oh, look, okay, I got momentum, I got mass, I can say P is equal to mv, solve for V, it's P over M, and then take that number and plug it into there. How many people did that? Okay, that's fine. That is absolutely fine to do. But if you take a step back from it for a second, what are you doing? You're dividing momentum by mass, and then you're trying to get momentum back by multiplying the velocity by mass. So why don't we just do this? Why don't we just say 0 plus negative 18? We know what mv is. They told me in the question. mv, the momentum, is 18 to the left. We don't need to find velocity and turn around and multiply it by mass again, although we can do that. It's just extra work. Just use the momentum that they give me here. Now we're looking for the momentum of the combined masses. Just say PF. Forget about mass and velocity, just PF. The final momentum, x direction, is negative 18. Remember this. Remember this, please. One of your questions on your test on Monday. I won't be here for your test on Monday. One of the questions that people always ask me about. I'm not going to tell you exactly what the question is, but what I'm about to say might help you with this. Okay. Whether it's one-dimensional or two-dimensional, the total initial momentum will always be equal to the total final momentum. There's nothing new there. We've said that how many times? But just think about that, okay? The initial momentum in the x direction was 18. That's it. This guy didn't have any. What's the final momentum in the x direction? 18. Okay, we didn't really even need to go through this process. Think about that. Okay? You could see that there's one object with a momentum of 18 to the left. The final momentum had to be 18 to the left, regardless of all this work that we're showing here. All right, let's do the y component. Pi is equal to Pf again. M1 V1I plus M2 V2I equals MVF. M1 is 4 kilograms. Do we care? No, we don't really care right now what it is. Because I don't want to find velocity and then turn around and multiply my mass again and get momentum that I already have. Okay, the momentum is 11.2. The momentum of this one is 0 because it's all on the x-axis and we're looking for the y component there. The final momentum, oh, it's m times v, but m times v just equals p. So the final momentum y component is 11.2. The initial momentum in the x direction will equal the final. And there was only one object going on the y-axis, so that's what it is. Now let's combine those. 18 to the left, 11.2 upwards. We can find that resulting, not speed or velocity this time, but the resultant momentum this time. So not speed, but p will be equal to the square root of 11.2 squared plus 18 squared. And we can find the angle of that by using the inverse tan of opposite over adjacent. Jason, does that make sense? My solution is quite a bit shorter than some of your solutions because some of you guys went and calculated velocity, right? That's okay. That's okay. Yeah, I'm not going to look down on you because you took a little bit longer to do the question. That doesn't matter. But some of you probably did it even quicker than me because some of you probably recognized it. Wait a second. The initial momentum is 18 to the left and 11.2 up. The final momentum has to be 18 to the left and 4 up. Some of you probably went straight to this. Did anybody do that? Brendan? That's okay in a case like this. Okay, it's a straightforward one where there's only one object X and one object Y. That's okay to do that. What did you get, Brendan, by the way, for this? 21.2? Okay, what have I just found there? The final momentum, right? Here's a question for you. What's the initial momentum? $21.2. It's the same as the final. Okay? We calculated the final momentum, but it's the same as the initial. Had I just calculated the initial momentum by combining those two right off the top, it would have given me the final as well. Sorry, that's not quite the final momentum. The final momentum also includes an angle, right? As does the initial. So we'd find theta by saying the inverse tan of opposite over adjacent. Whatever that angle works out to be. That's the angle of the final momentum. It's also the angle of the initial momentum. How would you find velocity from that, actually? Because that was the second part of that question, I think. How would you find velocity from that? Some of you guys would already have it because you found the velocities as you were going, right? Stephen? Yeah, just use P equals mv there instead. Question 4 was the other one. A 400 kilogram bomb sitting at rest on a table explodes into 3 pieces. Here's where the explosion point is, okay, where everything starts blowing up. We've got a 150 kilogram piece moving to the east. We'll call that piece number 1. We got another one going 200 meters per second at 30 degrees south of west. Call that number 2. Where's my third piece go? I'll tell you what. I know partially where it goes, for sure. But the other component of it, I don't actually know. Which one do we know for sure? John, you look like you're ready to raise your hand there. Yes, we know that it's going to go north. We have a momentum to the south. It's got to go to the north. But the question is, does it go north and west, or does it go north and east like that? In all likelihood, it's going to go like this. We actually don't know that for sure. It depends on what's bigger, the x component of this or this. And we don't know that yet. Okay, let's figure it out. That mass is going to be, what, 150 kilograms? 400 kilograms minus 100 minus 150. Got a funny angle here. I don't like it. Let's go off to the side here. 30 degrees, x, y, 200 meters per second. Now we're going to have to actually go down in question number 5 to get some space to solve this. See what I've done there, guys? All I've done, really, is taken away this. Instead of going down at 30 degrees, now I've got one that's 173.2 to the left and 100 down. Not solving 5 here. This is still number 4. We have 0 initial momentum because it's at rest. It's before it explodes, right? After it explodes, there's 3 pieces. M1 V1F plus M2 V2F plus M3 V3F. Or if you already had the momentum given to you, then just put in P1, P2, P3. V1F is 150. What was mass 2? 150, I think, wasn't it? 100? Okay, thank you. V2F? Who's got this one? Wayne, you got that one for me? V2F for the x component. I'll give you a hint. It's negative. Yes, it's good. Negative 173.2. And M3, we said, I think, was 150. Okay, solve for V3F. Doesn't really matter what it is. The hard part's done. For the y component, 0 is equal to, the y component of the first one is 0. The second one is 100 times negative 100. The third one is 150 times V3F. Solve for V3F for the y component. And then combine them using your right angle triangle, using the Pythagorean theorem and the inverse tan function. All right, what I'd like you to do right now for the next little bit here is continue working on that worksheet. You've got 4 more questions on the worksheet. I'm not sure that I'll give you all class to work on it. We'll see how it goes. But I'd like to see what you can do at least with the next couple of questions. So let's get to work on that now, and then if I need to check one over here in a few minutes, we'll do that.